This is the Burns Harbor plant of Bethlehem Steel Corporation as it looked in June 1973. Major building groups are A, slab storage buildings, B, 160-inch plate mill, C, 80-inch hot sheet mill, D, 80-inch cold sheet and tin mill, E, cold rolled sheet shipping building, F, tin plate shipping building, G, tin plate mill, H, deepwater dock, I, basic oxygen furnace shop, J, blast furnaces, K, slabbing mill, L, power station complex. The coke ovens are off to the left and could not be shown in this view. Burns Harbor was built in several steps. The initial development provided finishing facilities for steel slabs. The next step provided coke ovens, a blast furnace, steel-making furnaces, and related facilities. The third step enlarged existing facilities, added a second blast furnace, and more coke ovens. Additions made since 1972 include a continuous slab caster and a sinter plant. This is the site of the Burns Harbor plant of Bethlehem Steel Corporation as it looked in December 1962. The tract, which Bethlehem began acquiring in 1956, contains about 3,300 acres. It is located in northern Indiana, along the south shore of Lake Michigan. On December 3rd, 1962, Bethlehem announced its intention to develop, step by step, a large-scale steel plant here to be known as the Burns Harbor plant. In the heart of America's Midwest, close to the city of Chicago and midway between Michigan City and Gary, Indiana, Burns Harbor is ideally situated. The tract has about 1 mile of lake frontage and is served by railroads and highways on the south, a power generating plant on the east, and a deep water port on the west. The plant was constructed in several phases. Built in the first phase were a plate mill, facilities for producing cold rolled sheet and tin plate, and a hot sheet mill. The task of building a steel plant on this rugged terrain was challenging. The tract was covered with heavily forested sand dunes, which rose to elevations as high as 120 feet. Between the dunes lay large swamp areas filled with saturated organic deposits and water. Construction began in December 1962. Engineers laid their baselines and bulldozers moved in to clear away trees and brush. Walsh Construction Company was named as initial clearing and grubbing contractor and later awarded contracts for foundation work, grading, and site preparation. Their first task was to clear the vegetation and install work roads to move equipment into and around the dunes and swamps. The largest swamp was an area called Mud Lake. Here, a sizable body of water rested on top of the organic peat, some 30 feet above the elevation of Lake Michigan. The primary mill area encompassed about 550 acres. Mud Lake and other swamp areas shown in blue covered much of this area. A temporary drainage ditch was dug from the mill area north to Lake Michigan to drain this surface water. Self-propelled earth movers, called pans, were the prime vehicles used for grading. The pan has a movable blade, and in ordinary soil conditions can drive and fill itself. Here, however, one and often two bulldozers had to push the pans through the sand in the filling operation, dropping off when the pan had sufficient traction to proceed alone. When the ditch was complete, bulldozers and drag lines opened the way for the water of Mud Lake to drain into Lake Michigan. Some areas were slow to drain, and the bulldozers and pans frequently were required to deepen the ditch, removing material that impeded the flow of water. The drainage ditch followed the eastern boundary of Bethlehem's property adjacent to the power plant of Northern Indiana Public Service Company. When finished, the ditch was about 3,000 feet long and 24 feet wide. While the swamps drained, drag lines began to remove the organic peat from the lake bottom. The contractor quickly discovered that the drag line buckets had a limited effect on the muck. It was essential that all of the peat be removed from the swamp areas and replaced with firm sand, since all mill foundations are soil-bearing. A bulldozer pushed a sand dam out into the swamp to keep the muck from flowing back, while pans brought fresh sand in behind the dam. The sand was mixed with the peat to improve the consistency of the material and make it more manageable. The dragline buckets used to remove the sand-peat mixture had capacities of 2.5 and 3 cubic yards. This method of mixing sand with peat proved to be far more efficient in the use of the contractor's equipment. The mixture was loaded directly into trucks by the drag lines and then hauled to 4 designated dump areas located outside, but close to the primary work area. The sand-peat mixture was later brought back and spread over the area surrounding the mill buildings and planted in grass. This use of the peat provided a fertile field which supported vegetation without the need to install an extensive irrigation system. More than 200 acres of sand were successfully stabilized and beautified by this method. Grading of the mill area progressed eastward from the western end of the site. Engineers determined that the finished grade should be established at 613 feet, some 33 feet above the elevation of Lake Michigan. That meant leveling the dunes and filling in the low areas. Like large beetles, the pans climbed the dunes and were shoved over the top by bulldozers. On their sliding descent, the operators dropped their blades, letting the momentum of the machines fill the pans. This method minimized the chances of stalling in the sand as they moved to the areas to be filled. Without breaking stride, they rolled over the expanding plain, depositing their loads in 6-inch layers, gradually building up the surface to the proper elevation. Behind the pans came compactors, tamping and vibrating each layer of sand to achieve desired soil-bearing values. From morning till night, and frequently around the clock, the fleet of machines crawled over the mill site, paring away the dunes, filling in the swamps. In the process, they moved and transferred 5,800,000 cubic yards of sand. Where the slopes were gentler, and as a time-saving device, mobile conveyors were also brought in to load the pans. As bulldozers shoved the material into the conveyor, the pans shuttled under it to load 30 tons of sand in 15 seconds. To connect the construction site with the railroads to the south, a cut was made at the extreme western end of the mill area. Here, the cut ran through several high sand dunes. As soon as the proper grade was established, another contractor moved in to lay the ties and rails needed to bring construction materials to the job site. Sandstorms plagued the builders. Often the men came to work in the morning, only to find that yesterday's lengths of track had disappeared beneath the rapidly shifting sand. The westernmost portion of the construction site was set aside for the contractors' use. Here were located the mobile offices, parking areas, supply depots, shop fabrication and repair facilities for the job. The foundation contractor erected a concrete batch plant with a capacity of about 200 yards of concrete per hour. All foundations for the mill buildings at Burns Harbor were soil-bearing, eliminating the need for bearing piles. However, the groundwater level was relatively close to the surface, so extensive dewatering was required to construct the massive foundations at their proper depth. A series of deep wells were drilled outside the periphery of the mill buildings to remove water from the general construction area. 33 such deep wells were driven to a depth of about 100 feet for the initial construction phase. 14 million gallons of water daily were pumped out of the mill area, and that was only part of the solution to the problem. When the lines for the large building foundations were established, the contractor used the versatile dragline to excavate the sand. Here, the foundations are being dug for the first of the 84 buildings to be constructed at Burns Harbor. The groundwater problem also had to be approached through the use of well points. In well point dewatering, small diameter pipes were inserted into the sand around the area to be excavated and connected to a larger main. Pumps pulled water from the immediate vicinity of the foundation like an irrigation system in reverse. Here, the well points clearly can be seen lining the excavation. With the working area dewatered, the workmen constructed wooden forms for the concrete. About 1/2 million cubic yards of concrete were poured into foundations in the first phase of construction alone. That's enough concrete to pave a 20-foot wide highway over 200 miles long. It is ironic that despite the presence on site of great quantities of sand, all of the sand used to make the concrete had to be brought to the construction site from southern Indiana. The native sand was too fine. January 1964. Flying from west to east, we pass over the contractor's village at the western end of the mill area. Next comes the plate mill complex. 2 buildings are up for the slab yard, and the main mill building has begun to take shape. Further east, another section of the plate mill building is erected, and work is moving ahead. Now we approach the cold roll sheet and tin plate mill areas. Here, the main activity is excavation and foundation work. Steel framing for the mill buildings arrives by rail. 83,000 tons of structural steel were fabricated and erected in this first phase of construction. And the ironworkers who erected the steel building frames were followed by other contractors whose work had to be closely coordinated so that their operations could be dovetailed with the completion and backfilling of foundations. As soon as the building frames were bolted, painters came on the scene. The colors selected for Burns Harbor were brown, beige, and green to help the mill buildings blend with the surrounding terrain. After the painters came workmen to install the siding panels and the roofing. The construction force at Burns Harbor eventually grew to about 5,000 people. It was the largest privately financed construction job in the world at that time. While finishing touches were being put on buildings in one area, foundation work was going on somewhere else. Once the concrete had set and cured, the well points were withdrawn and the groundwater allowed to rise to its normal level. Note the protective waterproof coating applied to the below-grade portion of the foundations. Some sheet piling was used, not as load-bearing elements, but to serve as bulkheads for deep excavations. June 1964, flying south over the east end of the plant. In the distance, the plate mill is under roof. In the foreground are the buildings that make up the sheet and tin plate facility. Once the buildings are enclosed and roofed over, the foundation contractor moves back in to construct the foundations for the mills, motors, furnaces, and processing lines. The fabrication and placement of underground utility and service lines is a major part of the contract. Lines for cooling water, power, gas, fuel, waste, sewage, stormwater, all must be placed in proper sequence. Here, Route 12 is detoured around storm drain lines that will carry runoff water to Burns Ditch and the Little Calumet River. Some of the in-plant service lines are so large they dwarf the men who install them. This is an 84-inch water main running parallel to the hot sheet mill. November 1964. We're traveling south, past the east end of the plant. These buildings form the sheet and tin mill facility. The high building will house the continuous annealing line. Now we've turned and are heading west along the south side of the sheet and tin mills. In the background, the tin plating line, and here in the foreground are the shipping bays for cold rolled sheet. This is the plate mill from the south side going west. This one building is more than a half-mile long, 3,000 feet. The plate mill complex alone contains 900,000 square feet of floor space. Inside, electricians are checking out the mill motors and circuitry. Bricklayers build up the slab reheating furnaces, lining the shell with refractory material. Millwrights assemble the giant rolls of the mill stands. Meanwhile, at the eastern end of the plant, the cold reduction mill stands are in place. Box annealing furnaces are being assembled. The continuous annealing furnace rises 8 stories high. The framework of the continuous pickling line, 1,000 feet long, is taking shape. Steel slabs to feed the finishing mills at Burns Harbor were shipped from Bethlehem's eastern plants in unit trains. In December 1964, 2 years from the beginning of construction, the first slabs were rolled into steel plates at Burns Harbor. The cold rolling mill started operating in July the following year, turning out sheets for automobiles, appliances, and furniture. This is the head end of the tin plating line. The first tin plate was produced here in early 1966. Next into production came the hot sheet mill. This mill is computer controlled from slab yard to finished coil. Startup of the hot sheet mill in the third quarter of 1966 marked the completion of Phase 1 of the Burns Harbor construction schedule. But the construction didn't stop. A second stage, making Burns Harbor a fully integrated steel plant, was already going ahead. New facilities included coke ovens, a blast furnace, raw materials handling facilities, steel-making furnaces, soaking pits, a slabbing mill, and power station. A breakwater was built out in Lake Michigan, and the harbor suitable for 27-foot draft vessels was built. Again, the pans and bulldozers went to work moving sand, 13 million cubic yards of it, more than twice the initial phase, to establish the finished grade for the plant. Again, construction workers swarmed over the job site, building forms, setting reinforcing bars, pouring concrete. Burns Harbor today is a fully integrated steel plant, capable of converting raw materials into finished steel products. Altogether, more than 5 million tons of raw materials are delivered annually to the dock. Its 2 coke batteries deliver 5,000 tons of coke daily to fuel the 2 giant blast furnaces, which produce 10,000 tons of molten iron every 24 hours. The iron is refined in the plant's 2 basic oxygen furnaces, each having a capacity of 300 tons. And while we make steel at Burns Harbor today, we continue to build for tomorrow. A strand casting facility capable of converting 300 tons of molten steel to slabs in 45 minutes is now in operation. A sintering plant, another steel-making furnace, another plate mill, and another cold rolling mill are on the way. Today, Bethlehem's Burns Harbor plant is a model steel-making complex. It produces 4.3 million tons of steel each year for American industry. It provides jobs for more than 6,000 people.